Dr. Math Tech here, answering some of your questions. Today I'm going to do some t-tests. So I have a case study here that we want to look at. So let's say, for instance, we have a researcher wanted to answer the following question. What is the difference in students' computer anxiety based on whether or not they own computers? The researcher surveyed 92 undergraduate education students via an online survey. In the survey, the researcher asked a yes or no question to determine if students own computers. Participants' computer anxiety was measured using the computer anxiety scale. Scores range from 0 to 40, with higher scores reflecting greater computer anxiety. This variable was measured on the interval scale, and the research analyzed the data using what t-test. So with t-test, remember t-test is a test that actually tests the means. And what we normally doing is we testing to see if the means differ, what we call significantly, is what we normally be testing for with a t-test. But there are different t-tests that are appropriate at different times according to the situation. So in this particular situation here, we have to look at some of the assumptions here. In this particular t-test, the assumption is we have to look for, I think it fits really nicely for the independent sample t-test. And some of those independent sample t-tests, the one of the assumption is you have to have two groups being compared should be independent of each other, which I think we have here. Observations are independent when information about one is unrelated to the other. So when we mean by this means that one group of subjects provide data for one sample and a different group of subjects provide data for the other sample. Meaning that the individuals in one group are not matched with the individuals in the other group. And normally we do this through a random assignment of groups. The scores should be normally distributed, but the t-test is pretty robust. So you can get away with some not reaching all those assumptions of normality. But when we talk about normal, remember we're talking about a bell curve, meaning that the data fits a perfect, pretty close to a bell curve. The dependent variable must be measured on an interval ratio scale. Our independent variable here is going to be these test scores ranging from 0 to 40, so they fit that scale. And the independent variable should have only two discrete levels, while independent variable here would be whether you have a computer or not, and it does meet two levels. Either you have a yes or a no. So here, but again, we'll be using the independent sample t-test. So here in SPSS, I have my data already pulled up, and I'm going to look at, go to analyze, compare means, because remember it's a comparison of means, and I'm going to go to the independent samples T. Well, a couple of things I have to do here. Remember, my grouping variable would be computer ownership, or my independent variable, and I have to actually define that. So if you notice that there's two little question marks there. Well, if you go, I want to go back and show you something. Here in the variable view, I've already defined this data here. So if I click male, you see I have male is equal to 1, female equal to 2, that's in my gender. And if I click my ownership here, you can see 1 equals yes, you have a computer, 2 equals no, you don't. So that's already taken care of. So when I go back to data view here and show you, so if you see it's 1, 2, 1, 2 is all the way down here. I'm gonna define that, and that I'm gonna have 1, and I'm gonna have 2, so either you have 1 or you don't, and I'm gonna hit continue. Now I need to put in my test variable. I'm testing against your anxiety, so I'm gonna select that there, and I'll press OK. And as you see here, it computes it, and computed it here. And let's take a look here. All right, so what we're looking at right here is the groups. Some summary statistics here. We have we have 24 people that actually have a computer that own it, and then we have 68 who do not own it. Their means go 30, or their averages is 30.54 and 31.46. So if you notice there, they're pretty close. So I'm not feeling really good about this being a significant test. Standard deviation is 5.158 and 5.959. So let's go on down to our t-test. Now this part right here is a little bit more advanced. What I'm going to tell you is, remember we assumed that in our test, we just, since it's a robust test, we're assuming that the variances are equal. Well, this Levine's test for equality of variances is actually a statistical test that has been run out of what we call it maybe ad hoc testing that was run to make sure that that was actually the case. So if you notice here, this was an F statistic, which is 1.31, but the significant value or the p-value here is 0.255. Usually we use the cutoff for 0.05. This is well above 0.05, so we would accept the null hypothesis on this, and the null hypothesis on this would be assume that the variances are equal. So only thing we have to pay attention to would be this top row of information here. If this was 0.05 and below, then we wouldn't pay attention to the top one. We would go assume that they are not equal. But since this test is not significant, we accept type 1 error or the null hypothesis, and we'll read from there. So now to our t-statistic. So our t-statistic here is actually negative 0.668. Our degrees of freedom, DF, is 90. And our p-value here is 0.506, which is very, very high, or a lot larger than the 0.05 level of significance that we were looking for. So what we would say with our test here, that we would accept the null hypothesis, meaning that by accepting the null hypothesis, what we're saying is that essentially that these means are the same. I don't mean they don't have to be the exact same, but they do not differ significantly from a statistical point of view. All right, so let's talk about how that looks in a write-up. So if I wrote that up here, we'll be talking about this. Let's start from the beginning. Our assumptions. Assumptions in the independent sample t-test that two groups are independent of each other. The scores are normally based. The dependent variable must be measured on an interval scale. The independent variable should only have two discrete levels. The descriptive statistics here, we had n was equal to 92. That was our sample size with 24 yeses, with a mean of 30.54 and a standard deviation of 5.158. And we had a no equal to 68 with a mean of 31.46, or the standard deviation of 5.959. Our actual hypothesis, null hypothesis, was comparing the mean scores of subjects who identified themselves as computer owners to the mean score of subjects who did not identify themselves as computer owners. No significant difference existed in computer anxiety scores. The alternate, so you have the opposite there. Your alternate hypothesis is comparing the mean scores of subjects who identified themselves as computer owners to the mean score of subjects who did not identify themselves as computer owners. A significant difference does exist in computer anxiety scores. That was the opposite. So the testing of the independence here resulted in this statistic here. So we have our t, which is 90 here, is in the inside the parentheses, which is our degrees of freedom. Then we have our t statistic, which is negative 0.668, and we're saying that our p-value is greater than 0.05. So the decision regarding the null hypothesis is an independent sample t-test comparing the mean scores of subjects who identified themselves as computer people to the mean score of those who did not identify themselves as computer people. No significant difference was found, meaning that essentially the means were the same. And there's the reported statistic right here. The mean of the computer, was not significantly different from the mean of the non-computer people. I might want to put people in here. Sorry about that. Therefore, we accept the null hypothesis, meaning that we're going to accept the null that this part is true, that there's no significant difference. So it doesn't. So what we're saying at the end of the day, it doesn't matter if you have a computer or you do not have a computer. Uh, if you have one or you do not have one, but essentially your computer anxiety is the same according to this data set we have. I hope you learned a lot. Remember, this is Dr. Math Tech. Like the video, leave a comment. Anything else you want to see, let me know. I appreciate it. Have a good one. Bye-bye.